Good morning everyone. I am Punityan. So today I will be taking up a topic that is moment of inertia. So moment of inertia is one of the important properties of a structural element that every civil engineer should learn. Okay. So today let me start with the moment of inertia. First of all, I will be taking up the definition of moment of inertia. So what is moment of inertia? It is defined as the resistance offered by an object to change in its rotational motion. In simple term, it is the resistance offered by an object to before bending. Okay. So before bending, what is the resistance it is offering? So that particular property is required to fix up the sizes of various structural elements. Okay. So what is moment of inertia? Moment of inertia is defined as the resistance offered by an object to change its rotational motion. Okay. So now in centroid, you people know that centroid it was given by area into distance, but in moment of inertia it is given by the formula area into distance square. So based on this, the unit of moment of inertia, it will be either mm to the power of 4 or it will be centimeter to the power of 4 or it will be the meter to the power of 4. Okay. Now one more important thing is centroid, we call that as first moment of area, first moment of area, first moment of area. Whereas the moment of inertia, we call it as the second moment of area, second moment of area, because of the formula. So for centroid it is area into distance. So that's why it is called as the first moment of area. Whereas for moment of inertia, it is area into distance square. That's why second moment of area. Okay. So now let me move on with the next thing. So next, let me do a derivation, that is obtain an expression, obtain an expression to find the moment of inertia of a plane area, of a plane area. So let me consider any plane area. Let me consider any plane area and let us try to find out an expression to calculate the moment of inertia. So for that, what I will be doing is I will be considering an object in the xy plane. I will be considering an object in the xy plane. So let me consider this as the x-axis and let me consider this as the y-axis and let me consider an plane area. Okay. So to obtain the derivation, I will be using a concept that is part to the whole. I am not dealing with the whole to the part, I am dealing with the part to the whole. So that's why what I will be doing is I will be calling the area of this particular diagram as area A, whereas I will be considering an elemental strip. So our elemental area, and I will be calling the area of that elemental area as dA. Okay. So now, so let me think that that particular elemental area it has a distance x from this particular point and this I will be calling it as y. This I will be calling it as y. Is that okay? So now let me go with consider an object in the xy plane as shown in figure of area capital A. So whatever the sentence that I am telling now, you people need to write it down. Okay. So consider an object in the xy plane as shown in figure of area capital A. Also consider an elemental area dA, okay, which is at a distance x from y-axis and distance y from x-axis as shown in figure. Is that okay? So now let me calculate the moment of inertia of this particular area about y-axis, okay, or about x-axis, anything is okay. So for that what I will be doing, the same formula I will be using. Moment of inertia is equal to area into distance square, but for the small area I will be going with. So let me write it down. So moment of inertia of the elemental strip about x-axis is given by so already I have told you people that moment of inertia is nothing but area into distance square. So that's why what I will be doing here is, so as I am calculating the moment of inertia of the smaller area, so it will be dIxx is equal to, where d represents the smaller moment of inertia, I mean the elemental strip smaller moment of inertia, is equal to area into distance square. What is that area? It is the dA into, what is that distance square? So I am calculating it about x-axis. So what is its distance? So it is y square, distance square. Let me call this as equation 1 for time being. So now I have calculated the moment of inertia of this elemental area about x-axis. But now what I want the moment of inertia for the entire area. So what we will be doing here is, the moment of inertia of the entire area is obtained by integrating equation 1. Please note it down. The moment of inertia for the entire area is obtained by integrating equation 1. So let us do that. So let me integrate it. So it is dIxx is equal to integral of, let me little bit alter it, it is y square into dA. So now what is integral of dIxx? It is nothing but Ixx. So Ixx is equal to integral of y square dA. So this is the formula that we will be using. So it is the moment of inertia formula for a plane area about x-axis. Is that okay now? So similarly, let me calculate the moment of inertia about the y-axis. So similarly, the moment of inertia of the elemental strip about y-axis is given by, so it is dIyy is equal to area into distance square. Area it will be saying into distance square. Now it is about y-axis. For y-axis, so what is the distance? It is small x. So distance square is x square. Let me call this as equation 2. So as we have already done the same concept, I will be repeating it. So the moment of inertia for the entire area is obtained by integrating equation 2. So that's why what will happen now? So it is integral of dIyy is equal to integral of x square into dA. So now what is integral of dIyy? It is nothing but Iyy, which is equal to integral of x square into dA. So this is the second formula that we will be frequently using it while solving the problems on moment of inertia or for any other derivations. Okay. So let me concentrate on two things, okay, which is the first one. So the first one is Ixx is equal to integral of y square dA. Iyy is equal to integral of x square dA. This is the first derivation that we have done now. Okay. So what is the name of that derivation? Obtain an expression to find the moment of inertia of a plane area by first principle or by method of integration. By first principle or by method of integration, or by method of integration. Or by method of integration. So this is the first derivation that we have completed. Let me move on with the next thing. So now let me move on with the next particular topic, that is polar moment of inertia. So let me move on with the next topic, that is polar moment of inertia. So what is that polar moment of inertia? If I calculate the moment of inertia about x-axis and y-axis, it is called as ixx and iyy. That is the moment of inertia about x-axis and moment of inertia about y-axis. So there is one more axis, yes or no? So x-axis, y-axis and z-axis. So if I calculate the moment of inertia of any plane area, so about an axis perpendicular to its plane. So think that an object has been kept in xy plane. Okay, so an object has been kept in the xy plane and I want to calculate the moment of inertia in a direction perpendicular to its plane, that is in the z direction, then that is called as the polar moment of inertia. So what is polar moment of inertia? Polar moment of inertia is the moment of inertia of any plane area about an axis perpendicular to its plane is said to be the polar moment of inertia. So for that also we have a derivation, it's a small one. Let me continue with that. So observe here, the same diagram I will be taking it, but here x distance, y distance is there, but I need the z axis distance. Z axis is towards you people. So what I will be doing is, that particular distance I will be marking it like this. That particular distance I will be marking it like this and I will be calling it as r. I will be calling it as r. Okay, so now what I will be doing is the same thing. The moment of inertia of an elemental strip about x-axis is given by, instead of this what I will be doing is the polar moment of inertia. The polar moment of inertia of the elemental strip about z-axis, is given by polar moment of inertia, whatever it might be, the formula is same, area into distance square. So polar moment of inertia, observe, it is di, about which axis I am talking about now, z axis, zz is equal to area, it will be the same for the elemental strip, into distance square. Now about z axis, so the z axis is towards you people. So I will be marking the z axis like this. So it is projecting towards you people. So area into distance square. Distance square I will be calling it as r square. Let me call this as equation 1 for time being. Next, for the same thing, if I want the moment of inertia for the entire area, then we need to integrate equation 1. Okay, the polar moment of inertia for the entire area is obtained by integrating equation 1. So what will happen, just check it out now. So integral of dizz is equal to integral of r square into dA. So what is integral of dizz? It is izz. So it is the moment of inertia about zz axis, that is polar moment of inertia, is equal to integral of r square into dA. This is one more formula that I want you people to remember. So totally we have derived 3 particular formulas. One is ixx is equal to integral of y square dA, iyy is equal to integral of x square dA. Now it is the polar moment of inertia, izz is equal to integral of r square into dA. So now let us proceed further. Now I will be moving on with the radius of gyration. Now I will be moving on with one more topic, that is radius of gyration. So it is the radius of gyration. So what is that radius of gyration? So I think you people know that. So whatever the objects that are available in the nature are not exactly the standard geometrical shape. Okay. So, whatever the object that are available in the nature, all are not of standard geometrical shape. So, it will be trapezoidal, right. So, what happens is, let me draw the diagram and then try to explain you people. So, let me consider that there is an object in the xy plane. Let me think that there is an object in the xy plane and the area of that is capital A. So, what I will be doing is, I will be concentrating this particular object and squeezing it and forming it a standard geometrical shape, and let me think that that standard geometrical shape is rectangle. So, now what I will be doing is, this is x, this is y axis. I will be concentrating this and I will be squeezing it and making it in the form of a rectangle, Please remember one thing, after squeezing it, whatever this entire area was there, the same area of rectangle needs to be formed, and I will be keeping that particular rectangle parallel to x axis, and I will be keeping that rectangle parallel to x axis, and the area of this should also be same as this area. So, now what I need to do here is, I need to place this particular object from the x axis at a distance in such a way that whatever the moment that this object was developing about x axis, area into distance, what is the moment that it was developing, the same moment should develop for this also. In such a manner, I need to keep that particular distance. So, after keeping that particular distance kxx, if I am getting the moment same for this object as well as for this object, then that particular distance is called as the radius of gyration. Even though it is a vertical distance, I have noted it, I denoted it with kxx, it is just a notation. So, it is the distance at which an object needs to be kept, so that this object should produce the same moment as the previous one. Okay, let me call this as diagram A, let me call this as diagram B. Let me write one more diagram for this. So, this is x, this is y. Now, what I will be doing? So, let me keep the object parallel to y axis. Let me keep this object parallel to y axis. The same object I have concentrated and squeezed it. So, whose area is same. So, area is capital A, and this distance at which an object I will be placing it, so that it produce the same moment as that of this particular object about y axis. So, that distance I will be calling it as, even though it is an horizontal one, I will be marking it as kyy. So, those distances are nothing but the radius of gyration. Okay. So, now I will be telling you people the same thing. So, what I am telling, consider a plane area of area A, okay. So, which is concentrated and squeezed and kept parallel to x axis as shown in figure B, such that this area will produce the same moment about x axis as that of this particular area. That distance is called as the radius of gyration about x axis and the radius of gyration about y axis. So, now what I will be doing is, let me obtain a formula for that. So, now the same thing. So, let me calculate the radius of gyration of this strip, okay, of this strip about x axis. So, what I will be doing? So, please write down that particular wordings. The moment of inertia of this strip about x axis is given by, so the moment of inertia formula is same, area into distance square. So, the same thing I will be going it. So, it is the moment of inertia of that strip about x axis is given by area is A only now, area into distance square, about x axis I am taking. So, the distance is kxx square. I want the formula for radius of gyration, where kxx and kyy are the radius of gyration about x axis and y axis respectively. Okay. So, now let me little alter it. So, it is Ixx by capital A is equal to kxx square, or else kxx is equal to square root of ixx by a. So this is one more formula that we will be using. So it is the radius of gyration of that particular object about xx axis is given by this. Similarly, shall we calculate it about yy axis also? So what I will be doing here is, so similarly we'll calculate the radius of gyration about yy axis, same thing. So radius of gyration, if I want, I need to take the moment of inertia about yy axis is equal to area into distance square. So area is same. So what is that? Capital A into about y axis I want it now. Observe here, about y axis I want it now. So what is that particular distance? It is kyy. It is kyy square, area into distance square. So now let me alter it a little bit. So Iyy by A is equal to kyy square, where kyy is equal to square root of Iyy by capital A. Okay, this is one more formula that we will be dealing with. This is one more formula that we will be dealing it. So now remember, totally 5 formulas we have derived. So one is for moment of inertia about xx axis. So which is that formula? Ixx is equal to integral of y square dA. So the second one is Iyy, moment of inertia about yy axis, is equal to integral of x square dA. Next we moved on with the polar moment of inertia. We moved on with the polar moment of inertia. So polar moment of inertia Izz is given by integral of r square into dA. Yes or no? Next, 2 more formulas. That is, the radius of gyration about xx axis is given by square root of Ixx by capital A, and about yy axis kyy is equal to, it is square root of Iyy by A. Now there are 2 theorems. Let me move on with the next topic. There are 2 theorems in the moment of inertia. There are 2 theorems in moment of inertia. So the first one is the perpendicular axis theorem. The second one is parallel axis theorem. So the first one is the perpendicular axis theorem. The second one is the parallel axis theorem. So let me take up the first one, the perpendicular axis theorem. Let me take up the first one. It is the perpendicular axis theorem. So let me take up that. So it is the perpendicular axis theorem. It is the perpendicular axis theorem. It is the perpendicular axis theorem. So the same diagram I will be considering it. So let me consider this as the x-axis. Let me consider this as the y-axis. In that particular axis, I will be considering an object of area capital A. In that, I will be considering an elemental strip. I will be considering an elemental strip of area dA. So the same thing. So this particular elemental area is at a distance x from y-axis, and it is at a distance y from x-axis. If I consider z-axis also, then it is at a distance r. Yes or no? So now observe here what I need to prove here. First let me write that. So in this, what I need to prove here is Izz. What is that Izz? It is the polar moment of inertia is equal to the sum of the moment of inertia of mutually perpendicular axis, that is Ixx plus Iyy. This is one of the important theorems that I want you people to remember. So what I need to prove here? So I need to prove Izz is equal to Ixx plus Iyy. So let me define it. So what does that perpendicular axis theorem states? It states that the moment of inertia of any area about an axis perpendicular to its plane, which is the moment of inertia perpendicular to its plane, it is the polar moment of inertia. So it states that the moment of inertia of an object about an axis perpendicular to its plane is equal to sum of the moment of inertia of the two mutually perpendicular axes. So let me repeat the definition by saying this. So the moment of inertia of any area about an axis perpendicular to its plane is equal to sum of the moment of inertia of an axis sum of the moment of inertia of mutually perpendicular axis. Okay, it is Ixx plus Iyy. So this I need to prove now. It's very simple. So what I will be doing is, I think you people know that the polar moment of inertia of an object about z axis is given by. So whatever the wordings that I am telling now, you need to write it down. Okay, the polar moment of inertia of a plane area about z axis is given by, you people know what is that, Izz, polar moment of inertia, is equal to integral of r square into dA. For time being, let me call that as equation 1. So now what I will be doing here is, I will be dropping a perpendicular from this particular line, and let me call this as O, this point as A, and this point as B. Don't you think that OAB forms a right angle triangle? Yes or no? So now what I will be doing is, consider triangle OAB. Next, applying Pythagoras theorem. Applying Pythagoras theorem. So I think you people know that what is Pythagoras theorem. So it is nothing but hypotenuse square is equal to sum of the squares of the adjacent side. I think you people know that the vertical one is y square. This horizontal distance is nothing but x square. So what I will be doing is, r square, hypotenuse square, is equal to sum of the squares of the adjacent sides. So sum of the squares of the adjacent sides. So r square is equal to, it is x square plus y square. Let me call this as equation 2. So now let me substitute equation 2 in equation 1. Okay, let me substitute equation 2 in equation 1. Then what will happen? Let us check it out. So it is Izz is equal to integral of, instead of r square, what I will be doing it is x square plus y square, okay, into dA. Let it be as it is. Let me rub that particular Izz is equal to Ixx. That is the one that I need to prove now. So now Izz is equal to, let me open that particular bracket. So it is integral of x square into dA plus, it is the integral of y square into dA. Okay, so now let me call this as equation 3. Now don't you think that we have seen this particular formula? Yes. So in the starting I have derived an equation. So we know that integral of x square dA is equal to Iyy. Next, we also know that integral of y square dA is equal to Ixx. So substituting this in equation 3, then what will happen? From 3. So from equation 3, so Izz is equal to, what is integral of x square dA? It is Iyy. What is integral of y square dA? It is Ixx. So let me slightly re-alter it. We already got it, but a slight alteration. Ixx plus Iyy. So now don't you think that this was the thing that we were supposed to prove? Izz, polar moment of inertia, is equal to sum of the moment of inertia about mutual perpendicular axis. So we are done with the perpendicular axis theorem. Okay, so now we'll move on with the parallel axis theorem. So now we'll move on with the next particular derivation, that is parallel axis theorem. Next we'll move on with the next derivation, that is the parallel axis theorem. So we have completed the perpendicular axis theorem. So now we are moving to the parallel axis theorem. So as usual, what I will be doing is, so first let me write down the diagram. So let me consider an object, and the centroid of this object, let me take it at the center. As usual, I will be considering an elemental area dA, and the entire area is capital A. So let me pass a line through the centroid, and I will be calling it as x. So now this particular elemental area is at a distance y from the centroidal axis. Think that you have one more axis parallel to the centroidal axis AB, and think that I want the moment about this particular line. Okay, think that I want the moment of inertia about this particular line. So that is nothing but the parallel axis theorem. Whenever you have two parallel axes, so I will be defining it. So let me call this as H. Okay, so any doubts in that particular diagram? So finally the total height it will be H plus y. Finally the total height it will be H plus y. So now let me tell you people, what is the final thing that we need to derive here. So it is the moment of inertia of any area about a plane, okay, about a plane is equal to the sum of the moment of inertia of a plane passing through the centroid and the product of area and perpendicular distance between the two parallel lines. So it is the moment of inertia that is passing through the centroid, sum of the moment of inertia passing through the centroid and product of area of that particular plane area into the distance between the two parallel axes, the distance between the two parallel axes, that is h square. So this is the thing that I need to prove now. IAB is equal to IXX, it is the moment of inertia passing through the centroid, plus the area of that particular area into the distance between, the square of the distance between the two parallel axes. Now let me state it. So it states that the moment of inertia of any area about a plane or about any particular line is equal to the sum of the moment of inertia of any area passing through its centroid and product of area and perpendicular distance between the two parallel lines. Okay, so this is how we need to deal with it. So now let me proceed with the derivation, because I need to prove that, right? So for that reason what I will be doing here is, so observe, so consider an area of capital A, also consider an elemental area dA which is at a distance y from the centroidal xx axis. Okay, so now what I will be doing here is, so you people know that now what I will be doing is the same thing. It is the part to the whole I will be dealing with it. So now the moment of inertia of this elemental area about AB line is given by, so please mark my words. So the moment of inertia of this elemental area about the AB line is given by, so it is DIAB is equal to area into distance square, the same thing, area into distance square. So what is that area? Area, I am concentrating on the elemental one, area is dA into distance square from here till here, it is h plus y whole square because it is distance square. Let me call this as equation 1. Now what I want the moment of inertia for the entire area about AB line. So it is obtained by integrating equation 1. It is obtained by integrating equation 1. So what I will be doing? So it is integral of DIAB is equal to integral of, let me alter a little bit, it is h plus y whole square into dA. Okay, so now what I will be doing, integral of DIAB is what? It is IAB. Now integral, let it be as it is. What is h plus y whole square? What is a plus b whole square? A square plus b square plus 2ab. The same concept I will be using it here. So it is a square plus b square plus 2ab into dA. Let it be as it is. Now let me open this brackets now. IAB is equal to integral of h square dA. H square I can take it out, it's a constant term, dA, plus one more is there, integral of y square dA. Let it be as it is, plus there is one more, that is 2h, I will be keeping it out, and y into dA. So let me call this as equation 2, I guess. Okay, let me rub this or let it be. So now what I will be doing here is directly, what is integral of 1 into dA? So integral of 1 into dA, it is capital A. So what is integral of y square dA? Integral of y square dA, the starting derivation. So integral of y square dA is Ixx. Done. Next, integral of y into dA. Area into distance square is moment of inertia. Area into distance, it is the centroid. But as we are dealing with the moment of inertia now, so centroid I will be taking it as 0. So from 2, what happens? So IAB is equal to h square into, what is integral of 1 into dA? It is capital A. Plus, what is integral of y square dA? It is Ixx. Plus, what is 2h? Let it be into, what is integral of y into dA? It is 0. So finally, a little bit alteration. So it is Ixx plus AH square. So whether we got that derivation? So what are all the derivation that we have done? To find the moment of inertia of a plane area. About x-x axis and y-y axis, both we have calculated. About x-x axis, it is integral of y square dA. About y-y axis, it is integral of x square dA. Next, we moved on with the polar moment of inertia and moment of inertia perpendicular to its plane. So polar moment of inertia Izz is equal to integral of r square dA. Next, we moved on with the radius of gyration about x-x axis given by square root of Ixx by A. Radius of gyration about y-y axis, it is square root of Iyy by A. Similarly, polar radius of gyration, actually I forgot to tell one more thing, there is one more radius of gyration, polar radius of gyration. So kzz is equal to square root of Izz by A. Okay, so now next we have derived one more perpendicular axis theorem. What is that? Izz is equal to Ixx plus Iyy. Okay, next parallel axis theorem. IAB, if I want the moment of inertia about a plane. Okay, so that is IAB is equal to Ixx plus AH square. Okay, these are all some of the derivation that I want you people to remember. So now let me proceed with some more derivations. So what are that some more derivation? While dealing with the centroid, okay, you people have found out some formulas for standard geometrical diagrams, for rectangle, for symmetric triangle, semicircle, quadrant of a circle. Similarly, here also we need to derive some formulas for triangle, rectangle and all those things. So we'll do it. Okay. Welcome back to the class. So let me continue with the next topic in the moment of inertia. Okay. So the next topic is, it's a derivation. Obtain an expression to find the moment of inertia of a rectangle about its centroidal axis by first principle or by method of integration. In the centroid also we have calculated the centroid about x axis and centroid about the y axis. Similarly, here also we will be calculating the moment of inertia about x axis and moment of inertia about y axis. So let me start doing the derivation. To do that, so first let me take up the heading to find Ixx. It is the moment of inertia about x axis. Okay. So now what I will be doing is, I will be considering the x axis and y axis. I will be considering the x axis and y axis, and I will be considering a rectangle here. I will be considering a rectangle here. So let me call that rectangle as A, B, C, D. And I will also call that, let the base of that particular rectangle be base B and depth be D. They have asked us to calculate it about the centroidal axis. I think you people know that. So rectangle is a symmetric diagram both in x axis as well as in y axis. So observe what I will be doing here. I know the centroid lies exactly at the center for this. Yes or no? So let me mark that also. So this is x axis. If I mark it in the vertical direction, that will be the y axis. So what will be this particular distance? So this will be d by 2. So what is this particular distance? This is also d by 2. Similarly, what will be this? b by 2. So what will be this? b by 2. So now everywhere it is the same thing. So I will be going with the part to the whole concept. So I will be going with the part to the whole concept. So what I will be doing, observe here. So I will be considering a elemental strip like this. I will be considering an elemental strip whose width will be same as this width. So that is B, and let me consider the thickness of that particular B, dy. And this particular strip is at a distance y from the centroidal x axis. Okay. So now let me repeat the wordings. I want you people to note down that particular reading. Okay. So observe, consider a rectangle ABCD in the xy plane as shown in figure of area capital A. Of area capital A. Area A. Also consider an elemental strip of area dA as shown in figure. Okay. So next what I will be doing, I want the moment of inertia about x axis. Yes or no? The moment of inertia of this elemental strip about x axis is given by, I always first go with the part then to the whole. So the moment of inertia of this elemental strip about x axis is given by, so it is d I x is equal to area into distance square, area into distance square. Okay. So now let me call this as equation 1. Let me call this as equation 1. Now what happens here is, observe, the moment of inertia for the entire area is obtained by integrating equation 1. Let me do that for time being. Before going with that, I want you people to concentrate on this wording dA. Okay. So what is dA here? It is the breadth into depth. So what is the breadth? It is B. What is the depth? It is dy. So let me write down that, where dA is equal to breadth into dy. So let me substitute this here and integrate it. Substituting the above in equation 1 and integrating at a time. So what will happen? Observe. So it is integral of dIxx is equal to integral of y square into what is dA now? So it is b into dy. Yes or no? But I think you people remember that whenever you do any substitution while integrating, so you need to apply the limits. It will become the definite integrals. So now, what is the limit that you can apply for this? So this it is Ixx, no doubt. Forget about this. Okay, and b is a constant term, let me keep it out. And it is y square into dA, let it be as it is. What is the limit that I want you people to apply? Think that you people are standing at the centroidal axis, centroidal xx axis. You need to complete the entire area. Okay, so then you need to go upward in this direction to complete this area, and you need to go downward to complete this particular area. So above higher limit is plus d by 2. So below limit is minus d by 2. So what should be the limit that I need to put? So it is minus d by 2 to plus d by 2. Now let me integrate it. So what is y square? Integral of y square, it is y cube by 3 into, it is d by 2 to minus d by 2. So first let me apply one by one. So it is y is d by 2 whole cube divided by 3 minus, let it be as it is. Next it is minus d by 2 whole cube by 3. So it is d cube, and what is 2 cube? 8. So it is d cube by 2 cube is 8. 8 3s are 24. Okay, minus. This is already minus. Minus d by 2 whole cube, it is minus. Minus into minus, it will become plus. Okay, so now it is d cube. What is 2 cube? 8. 8 3s are again 24. Let me take the LCM out of those two. It's 24 is the LCM. 24 ones are 1 into d cube, it is d cube plus 1 more d cube. So finally, Ixx is equal to, so it is 2d cube. And one more thing, I have forgotten this b. I have forgotten this b. Let me add that here. Sorry, I forgot it. So now it is b into 2d cube by 24. So 2 ones are 2, 12s are. So finally what is the answer? bd cube by 12. So please remember from now onwards, the moment of inertia of a rectangle about xx axis is given by bd cube by 12. So now what I will be doing is the same derivation. I will be altering it and I will be calculating it about y axis. Okay, just observe what will happen. So now I will be rubbing this. I will be calculating it about y axis. I will be calculating it about y axis. I will be altering the same diagram. So as I want it about y axis, I will be considering an elemental strip in the y direction. Please be careful. So I will be considering an elemental strip in the y direction. So let me say that thickness is dx. Okay, and it is at a distance x from the y axis, and this is the centroid G. So here also the same thing. Okay, so now what I will be doing is I will be calculating the moment of inertia of this elemental strip about y axis. So here instead of xx axis, let me call it as y axis. It is the same thing, area into distance square. What is the distance square here? So it will become area is dA. So this is dA into, what is the distance square about y axis? It is x square. Okay, where dA is nothing but equal to, so depth into thickness. depth is d, thickness is dx. Depth is d, thickness is dx. Substituting this in this and integrating equation 1, because this is for a elemental step. I want it for the entire area. So we'll do one thing, instead of altering everything, let me rub it and do it. It would be helpful, or it would be better. Okay. So now what I will be doing is substituting the above in equation 1 and integrating equation 1 to calculate the moment of inertia of the entire area about y axis. So now what I will be doing, it is the integral of diy is equal to integral of dA, I know it, what it is, d into dx into, so x square, and I need to apply the limits. Be careful with the limits now. You are standing in the y axis. You need to cover the entire area. So parallel to a y axis, you need to cover the area. If you go towards left, it is negative. So what is that? It is minus b by 2. If you go towards right, it is positive, plus b by 2. So it is minus b by 2 to plus b by 2. So out of this, which is the constant term, d I can take it out, and let me integrate x square into dx, or let me write down one more line. It is x square into dx minus b by 2 to plus b by 2. So this will become Iyy. So now it is x cube by, so let us not forget this time. So d into x cube by 3, and the limit is minus b by 2 to plus b by 2. Okay. So now d, let it be as it is. So this will become, first let me apply the upper limit. So it is b by 2 whole cube. So it is b by 2 whole cube divided by 3 minus, let me apply one more, or let me rub this. Okay. Let me apply one more. It is minus b by 2 whole cube divided by 3. So now it is d, let it be as it is. So it is b cube by 24 minus, minus and minus, it will become plus, because minus of whole cube, it will become minus only. So minus into minus, it will become plus. It is b cube divided by 2 cube is 8, 8 3s are 24. So now Iyy is equal to, so it is d, let it be as it is, 24 is the LCM. So 24 1s are 24, 1 into b cube, it is b cube only, plus 24 into 1, 1 into b cube, again it is b cube, so it is 2b cube now. So d into 2b cube by 24. So it is db cube by 12. Iyy. The moment of inertia of a rectangle about y axis is given by the formula db cube by 12. So please remember this. About x axis, it was bd cube by 12. About y axis, it is db cube by 12. Okay. So this completes the derivation of rectangle. Now we'll move on with one more derivation, that is the circle. Find the moment of inertia of a circle about its diametrical axis using the first principle or by method of integration. So we'll start now. So now observe here, I will be moving on with the next derivation, that is obtain an expression to find the moment of inertia of a circle about its centroidal axis or diametrical axis by the first principle or by method of integration. Okay. So to derive that particular expression, I have considered a circle which is symmetrical about y axis and x axis. Okay. So now the radius of this circle is capital R and the radius of this elemental strip is R, and the thickness of that elemental strip is dr. Okay. So keeping that in our mind, let me proceed. Now before going into the main thing, how to calculate the area of this elemental strip? How to calculate the area of this elemental strip? So what is that circumference? What do you mean by circumference? It is the outer entire length of that particular circle. Okay. So we have a formula, area of elemental strip is equal to, area of elemental strip. Area of elemental strip dA is equal to, okay. So now, will you people accept that it is nothing but the circumference into thickness? So it is circumference into thickness. It is the circumference into thickness. So now, what is the circumference formula for a circle? It is 2 pi r into thickness is dr. For time being, let me call this as 1. Now, again I will be going with the same thing, that is the moment of inertia. I will be going with the polar moment of inertia. So, polar moment of inertia of this elemental strip, okay, is given by dIzz is equal to area into, what is the area? So, for time being, let it be as it is, area into distance square. What is the distance? R square. Then what is the area? Just now we have calculated it. Area, instead of that, as I am dealing with the small one, dA I will be writing it. It would be better. So now, what is that dA? So dA is nothing but 2 pi r into dr into r square. And this, let it be as it is. It is dIzz, and I will be calling this as equation 2. Or else we'll do one thing. Let me realter a little bit. So it is 2 pi r cube into dr. I think this I can call it as equation 2. Now, the polar moment of inertia for the entire area is obtained by integrating equation 2. As I told you in the starting, I am using the concept part to the whole. So now, integrate it. Integral of dIzz is equal to integral of 2 pi, I think I can take it out, into integral of r cube into dr. Okay. So now, I think you people know that as I am using or I am substituting some value in the integral, so I need to put the limit. So it is 0 to, think that you are standing at this particular junction and you need to complete the entire thing. So it is r, 0 to r. So now, let me do it. What is dIzz? It is nothing but Izz is equal to 2 pi, let it be as it is for time being. Now, what is r cube, integral of r cube? It is r to the power of 4 by 4 and it is 0 to r. So next, it is 2 pi, let it be as it is. Let me apply the upper limit. It is r to the power of 4 by 4 minus 0. Or else, can I call it like this? Izz is equal to 2 pi r to the power of 4 by 4. Or else can I say it is pi r to the power of 4 by 2. So now the same thing, if I write it in terms of diameter, the same thing, if I write it in terms of diameter. Now, in terms of diameter, if I write it, so what this Izz will become? So it is pi into, radius is nothing but diameter by 2 to the power of 4 by 2. So or else can I write pi d4, 2 to the power of 4, 16, 16 into 2, 32. So Izz is pi d4 by 32. But what is the heading? Just check it out. Obtain an expression to find the moment of inertia. But I have calculated the polar moment of inertia. So now I need to calculate the moment of inertia. I will be rubbing this particular part. Now what I will be doing is, using the perpendicular axis theorem, perpendicular axis theorem. I think you people remember that. Perpendicular axis theorem. What is that? It is IZZ is equal to IXX plus IYY. Yes or no? Now, one more thing is IZZ, just now I have calculated it. It is pi d4 by 32. Or let me substitute it in terms of radius. Let me check it out once. So it is pi d4 by 32. Here also it is in terms of diameter only. So let me take it out. So it is pi d4 by 32, okay, is equal to. Will you people accept that? As it is a circle, the moment of inertia about x-x axis, the moment of inertia about y-y axis will be same, because in the x-axis also if I cut it, it becomes two equal parts. In the y-y axis also if I cut it, it becomes two equal parts, where all the parts are of same thing, area. So that's why what happens is Ixx, instead of YYY, I can write it as Ixx because it's a circle. So this will become 2Ixx, and this is pi d4 by 32. Now this, if it comes down, Ixx is equal to pi d4 by 64. So please remember, from now onwards, the moment of inertia of a circle about x-x axis is given by pi d4 by 64, and the same is for Iyy. So any difficulty in doing this?